So this is geospatial analysis techniques. What we're going to talk about, this is now spatial analysis with vector data, and we're talking about, for example, buffering, dissolving, we're talking about overlay operations, we're talking about attribute table operations, and we'll show you a bit about geocoding. I don't think geocoding is relevant to Mongolia, but we will tell you what we do with geocoding in North America. Basic geospatial data analysis. It's operations to manipulate and calculate coordinates and other related attribute data. That's the definition. For spatial data analysis, you require a number of things: input, operation, and output. Here, typical geospatial analysis techniques that would be examined in this: selection, buffering, dissolve, overlay operations, classification, table operations, and geocoding. Selection operations identify features that meet a condition. Selection conditions may be spatial or aspatial. Selection based on attributes is aspatial. Selection based on position is spatial. Table query. Table query is when we operate on the attributes. So the typical information that you would do in table query, for example, is using set algebra. You're doing a query on a value inside a table. You want all the points less than a value that has this value, less than something, greater than something, numerical, equal to, not equal to. Query is using set, okay, algebra. For example, you want to show all the male population that is greater than female populations in the United States. There are more cowboys than cowgirls so not enough women, and more men, all right? So men and horses, maybe, I don't know. This other one is all the states with population greater than 7 million. So California, 30 million plus, Texas, Florida, okay, and up the West Coast. So those are all dense states. The states in the middle are less populated. This is region that is not mountainous, doesn't have mountains. So in the states, this is the mountains. This goes up here. So the blue states are the ones that are more flat. So this is an equal. Where is South Dakota? The blue. So that's aspatial, not spatial, that's by name. So which state is called South Dakota? Where is South Dakota? That's where it is. So then you have set algebra and you have Boolean algebra. So Boolean algebra is or, and, not, and so on. It's true or false. These are tables, Boolean operations. A truth table allows us to see the results operation R in the table. We can apply input of X or X and Y.
So R is the result. So X is your X and Y are your variables.
Okay.
So if X is true, and you're using a not operand,
then
not
return the
true
false.
is false.
Yeah.
Not false is true. And the AND operator looks at X and Y, and a false and a false, the result is false. A true and a false is false because one of them is false. If X is false and Y is false, this is the same, it's also false. The only way that you get a true result when you use the AND operator is when both X and Y are true. And the last Boolean operator is OR. And you can see that in order to get a true result, at least one of X and Y has to be true. So true plus false is true, false plus true is true, and true is also true. The only way that you get a false result from the OR operator is if both X and Y are false, then the result is false too.
So combining set and Boolean operators. Focusing on the chart, okay, so what are we trying to test here? Let's see. Table reads parenthesis, you and me equals yes or no, member equals no, and unemployment greater. Spend a few moments, go row by row, and see if you can tell which countries are selected based on this query. So it's basically just unemployment greater than 3.5. So there are three of them that match that query: Pengo, Tempest, and Saxon. So this one, question is, you want population greater than 80,000 and unemployment less than 6. So the answer is, anybody guessing?
Wait.
There is no country that fits that criteria, I don't think. Let's see if it's right. No, that fits that criteria. This one here, so we want population that is not less than 1 million and greater than 31 and a member of the UN. Penguin, Zaxxon, and Galaxian. So spatial selection. Adjacency. All right, so these are topological terms. So these two polygons are adjacent because they share a boundary. Intersect is touching. Well, anything you could intersect, it doesn't have to be adjacent. You could have another object. Okay, these two intersect. And contains is basically is inside. Distance is within a set distance of a feature. This is really distances. Normally we use that for tolerance, how close. For undershoots and open shoots we would use distances. Okay, distance is like how close is this object to that object. This is the distance. So here's an example of a buffer. So we want to know what a buffer is. So this is the object. We want to create a buffer. So we want to have a buffer distance. We want to create this buffer on the outside. So an example of a buffer. Say you have a power plant and you want within 1 kilometer of the power plant. Okay, so you create a buffer and you don't allow any buildings near there because of pollution. Another example of buffer could be if you have an international airport boundary, you want to buffer so many kilometers before you can have a high rise. Another example is you could have a protected area and you want to have a buffer before you can have a mining claim near the protected area. You might have a buffer of 500 meters before you can have a mining claim license.
You evaluate the true or false of the statement inside the parentheses, and then you do the rest of it. So population less than 1 million and population greater than 31,000. So you evaluate that first. Well, so that's not Pengo and not Tempest because their population is too high. Greater than 31,000 means not Zaxxon either because that's too low. Galaxian, that's a little bit too low because it's 30,167. So that one is the only one that fits the population. So that's inside that. And then when you apply not to it, because not is the order of precedence for evaluating, not is higher precedence than and. So you evaluate this next. So if you look inside the brackets, that's the only one that matches when you say not that.
Rest of
then
them.
you mean these four.
Uh-huh.
So not that is these four.
Mm-hmm.
And then and, so that's the
3 yeses.
3 yeses.
Dissolve. So this is an example of dissolve. You have states and you're trying to say, well, are you selecting, breaking down northern and southern states? Once you're finished, you can dissolve the boundaries of the states. So you just have north and south. So you just make it one big polygon instead of many small polygons. So overlays is when you're combining spatial attributes for one or more data areas. So one of the really key things, and it took me a little while to remember sometimes, is that the most critical thing here, I used overlay operations and I found, oh, it doesn't work. And I'm scratching my head, why doesn't it work? The 2 polygons are there. It turns out that they were not in the same coordinate system. So for overlays to work, so you have to be careful. I would turn off on the fly, okay? Because in QGIS, even if the two layers are different projections, they will show in the project coordinate reference system if you have on the fly. And so you think these 2 layers have the same projection, and they're not. And if that happens, the overlay will not work. On the fly, it makes everything in the same projection. It looks like it's the same projection, but they may not be. And if they're not, then it won't work. They have to be on the same coordinate references. I mean, for example, you have one layer in UTM zone 47. You have another layer in lat long. You have your project coordinate system in 47, UTM 47, and you enable on the fly. So what you will see is the lat long layer will be displayed in UTM 47, but the data is still lat long. The coordinates are still lat long. So if you try to do an overlay, it won't work. So vector overlays. Clip functions. So these are different overlay functions. So clipping layer, you have a polygon, you have data, the road network, and you only want to see roads inside this polygon. So you would clip the roads, the polygon, and get just the roads inside this area. Input, operation. For example, this is roads of all of Mongolia. This polygon is your SUM. Or your IMAC. So you say, I don't want all the roads of the whole of Mongolia. I only want roads in my IMAC. Roads in all of Mongolia, my IMAC, I clip it, I only got roads in my IMAC. Intersection, so again, same kind of idea. You have two polygons, you just want where the two intersect. And this is overlay union. So union is similar to the other one, except that you're combining. So in the middle, this is A, this is B. You want to create a polygon that is both problems. In many cases, and this is very common, say you have two bag districts, and you digitize this from a map. You digitize bag 1, bag 2, all right? And you think this boundary, because you did it twice, you digitize this bag first, and you digitize this one. It looks like it's one line, but it is not one line. So what happens is you actually have sliver polygons. It's not the same boundary. It is two boundaries that are close, but not the same. So you may have gaps and you may have slivers. So they may have come from two areas. That may be the boundary of two SUMs, and one SUM digitized one side, the other SUM digitized the other side. And then when you combine them, you find that they overlap. Very common. Boundary problem is always very common. In terms of that problem, I mean, we can clean it, but it's what we call data cleaning. Part of the problem occurs because you have slightly different geometry. The different geometry creates slivers, and you get slivers because you're manually snapping the digitized boundaries, and sometimes it's not very clear. You may have overlap and you may have gap. The other ones is intersect, union, and join. You have two tables, and you want to find, these are the intersect fields that are matching. So these are not spatial, this is what they call aspatial intersect. So out of the two tables, there's only two records that are common in both. And if you combine two tables, you have one table. That's a union. Join. Here's an exercise on joining. If you have one table and you want to append information from another table, you do a join. So databases join, you can only join if you have a unique common field or column. So in this case, these two tables are joined using the region. So geocoding, I don't think Mongolia would have an application, but back in North America, we have what's called linear and area geocoding. So the geocoding is you have a house there. So for example, we have house street number 100, 200. You want to automatically assign a number to the house based on the location along that street. So geocoding would take the starting number, ending number, do a mathematical computation and say that house number should be 180 because it's about 80% from here to here. It's 0.8 of the line. So I mean, part of this is if you imagine in North America had a big grid, which is these section lines, okay? These subdivisions, so we have houses here, okay? And basically what happens is that you have this is a rural road. And part of the geocoding kind of came from, a farmhouse here, farmhouse here, farmhouse here, farmhouse here, okay, for example. And in many cases, the rural counties or bags or whatever it is says, okay, we need to know if somebody calls and says there's a fire. It's very hard to find this house, okay? So what happens, they're saying, well, okay, let's have a system, so we would make this some kind of a road, and between each of these we assign a number. Okay, so this is, say, rural road number 1. Rural road 1, okay? And I'm going to start here, is 1,000, This block is 2,000. This block is 3,000. All right? Now, I want to use GIS to give these houses numbers. Okay? So theoretically, you could have say in my house numbers, I theoretically can have 100,000 houses between here and here. Okay? 1,000 house numbers, right, theoretically. And if I go by 10, I can have 100 houses. Yeah?
Mm-hmm.
So there's only one house here. If I give this a number, I'm going to make room for other houses when they come to get built later on. Right? So I take this 1,000. I see that this is around 100 meters from the end. So I make this number 1, 0, or 1, 1, 0, 0. And for this segment, then this house is approximately, again, say 10% up. So this becomes 2, 0, 1, 0. Okay? This may be 50% up, so I name this 2500 or something like that, and this could be 2800. Okay? By apportioning the distance. So that way, if there's a fire, and then they say I'm in Rural Road 1 and I'm at 2500, the fire truck knows where to go. This is similar idea. This is area geocoding. Area is by zone. So again, this is mainly to do with addresses. So area geocoding, they don't care about the location. I don't think that there is any logic there. Okay. Those, they're just assigning numbers to the buildings in their location rather than along a line. Okay, so they're not doing any spacing. Okay, so the difference between the linear geocoding, the geocode actually tells you a location. So the linear geocoding, when you say the buildings are 180, it actually means that it's 80% down the line. Area geocoding, so area geocoding just means that in this area, the buildings go from 100 to 200, the numbers. There's not a location specific. So 110 is not 10% from this intersection. Okay, and that's it.